Hello children, today's class we will talk about resistance, resistivity and resistors, then resistors in a series connection, resistors in a parallel connection. So before we start this, what is resistance? In detail, we will do activity 11.2 from your textbook. You see what is the activity says? Could see there is a circuit diagram given. So what is when you look at the circuit, it's a basic circuit given, and we know this is the key or the switch. We know this is the switch. If there is a dot, it's called as enclosed. You should always have a closed circuit. Then this is the cell, or we'll call it as combination of cells, or we'll call battery, combination of cell, or we'll call it as battery. So this battery, we know that the current flows in a circuit only when there is a potential difference created. So the potential difference in a circuit is created by the battery. So this gives us a potential difference. So if I connect the voltmeter here, it will give me the what is the potential difference. For example, it may give us 6 volts, for example. So this is the purpose of the battery or the combination of cells. Then A is the ammeter, which is going to give me the I value. So this is the circuit or the metallic wire. So in activity 11 point, this activity is, what is this activity mainly for? This activity is mainly to say that different materials or different substances will carry different current, or it will show a different ammeter readings. So that is, current is different for different components. That is what this activity in figure 11.4 shows. That is, current is different for different materials. First, let us take this nichrome wire. So if I connect here in the gap given here, so this, when I check the current I, so this will give me, consider it is giving me 3.5 amperes. Then instead of this wire, if I take the bulb, and if I'm going to connect the bulb here, if I connect the bulb here, so the bulb may show me the current of 4 amperes. Then instead of the bulb, if I'm going to connect this torch bulb here, so that will also, this is the torch bulb. If this is the torch bulb, this also will show me a different current. Consider it is 4.5 amps. So come to the last point. Are the ammeter readings different for different components connected in the gap XY? Yes. What do these above observations indicate? It indicates that the current is different for different components. So whenever we are going to attach different substances, each component will give its own current readings. So this is what inferred from this activity. So now, based on this observation only, we know that there are different type of materials. That is, we have the what are the different components? Different components, we say it is a conductor. It can be a insulator also. So in a conductor, we know it allows the current to flow easily. So it gives for current, it gives an easy path. For the insulator, it will resist, this insulator resists the flow of current. For the same reason, we use the conductors in the circuit. That is the reason we use the metallic wire as a metal, example a copper wire. Then now we will come to the main topic. What is the resistance? We already know that resistance is the property of the conductor. So you have any conductor, the conductor is going to show a resistance already, which we saw it in the Ohm's law. It says clearly that the resistance is given by the conductor, each conductor gives the resistance. You see, resistance is a property of a conductor. So each conductor will have the property of resistance. The property of resistance is nothing but it will resist the flow of current. So one understanding the resistance, where do you find this resistance? I find in conductor. You find it in a conductor. Then this resistance, what is its function? It is going to resist the flow of current. If that is the case, but in the case of conductors, the resistance will be very low. So in a conductors, the resistance will be very less, or it will be very low. Now, in case of insulator, what about the resistance? Insulator will have a high resistance. It will have high resistance. That is the reason insulator, I don't call it them insulator. The objects showing high resistance, I will say them are poor conductors. So insulators, I also call them as poor conductors because they show high resistance. When any high resistance is there, obviously the current will not flow in that circuit. For the same reason, we are using the conductor. Okay, fine. So now, this conductor, we know it is going to show a resistance. That resistance will be very less. Suppose if I want to use a different type of resistance. Suppose resistance is given by the formula. What is the formula for the resistance? We know V is equal to IR. From this we know R is equal to V over I, and this ratio is always constant. And what is the unit of resistance? It is going to be ohm, or it is going to be volt, V for and ampere, volt ampere, but generally we are going to use the unit ohm. Fine. So if I want to use a different resistance, I don't want the resistance given by this conductor. For example, let us just take one circuit. Let us take this circuit. So this circuit, you see, here this is the cell. This cell mainly it is for creating the potential difference. This is the ammeter where I used to measure the current. This is the switch saying that it's a closed circuit. Fine. Then where is the conductor here in this circuit? So this metallic wire is basically a conductor. So metallic wire is going to be basically a conductor. We know that. So if I want to show the resistance of the conductor separately, what do? I show with this symbol. So now this is a symbol for resistance, and if there is a device which can give a resistance, is called as the resistor. If you do not want the resistance, if you are thinking that okay, this conductor itself, this metallic wire itself, it is going to give me a resistance, but this resistance will be very less, but I want a more resistance. What is the option for me? What I will do? I will take a resistor and I will fix it in the circuit. So this resistor is nothing but a device which is going to give me the resistance. So for the resistance and the resistor, same symbol is used. This symbol is used. Now, so whenever the resistance is there, whenever I have a resistance, it is going to resist the flow of current. The resistance will always resist the flow of current. So let us see what is this resistance. So now I will show you a circuit diagram where I use a resistance also. So for example, you see, I have a cell, then I have this ammeter, so from this ammeter, consider there is a switch, and from here I have the resistance, then I have the 2 points where I will connect the material. So we know, as soon as I see this symbol, I know this is a resistance or resistor which is going to oppose the flow of current or resist the flow of current. Then whenever there is a resistor, we know we can calculate the potential difference. So for any given resistance, there I can connect a voltmeter, I can find the potential difference. So across the resistance coil or the resistor, you can connect a voltmeter and you can find the voltage difference or the potential difference. So even here I can get a potential, I can connect a voltmeter and find the potential difference here. So here also I will connect the voltmeter and find the potential difference. Why? Because here this cell will initiate the potential difference for the circuit to work. Here the resistance, when the current comes here, when the current flows here, what happens? It finds a resistance. So what happens when it finds a resistance? When the current is coming this side, when it finds a resistance, so the flow of current will be resisted. No, this resistance will stop the flow of current. No, that means the current value will change. No, when the current is moving across this resistance, current value will change. When the current value will change, obviously there will be a potential difference. The volt also, V also will change. No, that is the formula. No, because V is proportional to I. Whenever there is a increase or decrease in I, V also changes. That is the reason wherever you find a resistance, I can connect a voltmeter, I can find the volts also or the potential difference also. So next we move on to an important topic, that is the factors on which the resistance of a conducting wire depends. So we are going to talk about the next topic, the factors on which the resistance of a conductor depends. So we will understand this through an activity. So we are referring to the activity 11.3. A circuit is taken. So according to the contents given, the details given, I write a table, that is first you see marked one. You see, I will take between these 2 points, I keep different types of wire of different composition. So you see, first one, when I place 1, this is the wire number, this is the wire number, then I will understand what will be the current. When I place this wire, what will be the current, then I will understand what will be how the resistance change, what will be the resistance R. So here first I take first the wire number 1, wire of length L, and there is a cross section area. It's a normal wire of normal length and cross section area A. So the wire 1 has length L and consider a cross section area A. What is a cross section area? You see, if this is the wire, if this is a normal wire, this portion is the length L. This circle part is there, no? This is called as the cross section area. This is called as the cross section area. So which is a circle basically. So we'll use the area of a circle, which is nothing but pi r square. This is cross section area. So now I taken this as A. Now what will be the current? When I consider the current here is I, and R will be given by, R is V by I. It's given by V by Y is equal to R. Now second wire, what is the difference I do? Second wire, I increase the length. You see, that is 2L. I take another wire of same area, same thickness, but twice the length. That is, here the L is 2L, but same cross sectional area. So cross section area is also referred as thickness. So cross sectional area, it's also the different other word is, or I will call this thickness as the cross section area. So L is 2L and the area is the same. So when the length increased, what did I notice is the current also, when the length increased, the current also increased. You see, the second number 2 wire, we say the length is increased. So the length is increased, then what happens? Here in number 2, as the length increased, we found that the resistance also increased. Here in number 2, wire number 2, the length when become 2L, resistance also increased. R also increased. So when the resistance increased, obviously what will be the meaning? The current will flow very less, no? So my I became I by 2. Current was halved when the resistance become increased. What I did, I just increased my length. Instead of L, I doubled the length to L. So what happens here to the resistance? Resistance will be, you see, my resistance is increased, no? So how will I know? Here the resistance was R, here it is V by I by 2. This 2 comes to the numerator, it becomes 2R. You see, the resistance is increased. Because the resistance increased, current is halved, I by 2. Then I take the third wire. Third wire, what I do, mark 3, what I do, same length, L is same, but the thickness, I take a thicker wire of larger cross section area. I take a thicker wire. So my area is more in the wire. So now in the I continue the table here. So here the wire number is 3. Here L is same, but my cross section area is 2A. Okay. So now what happens here? So when this is happening, what will happen to the current? The current is doubled. I find the current is doubled. Why? I increase the cross section area, the current is doubled. But what about the resistance? It was V by 2I. You see, the resistance was halved. It is half R. Resistance became halved. Why when the cross section area is increased, why my resistance decreased? Only because the resistance decreased, there was more flow of current, no? The current becomes 2I. Why is that? This is because, as I said, how do I define the cross section area? Now I have taken a bigger cross section area. You see, the cross section, the area is more. The same length, but the area is more, cross section is more. This A is nothing but 2A. That means more space is there, no? So more current will enter, right? Look at this space. Here only I show current in one line. But here you see how many lines I have shown the current. So more the area, more the current flows in. Obviously, if the more current goes in, obviously the resistance will decrease. That is the reason when I increase the cross section area, my resistance decreases and the current increases. Then fourth number, what I do in the fourth wire, what I do, I change the material. Instead of taking a nichrome wire, I connect a copper wire. For it is here same length, same cross section area L and A, but here it is a different material. Material is different. That is, I have taken copper. So what I noted is the current increased. That means whenever there is a current increase, the resistance was less. V by I ratio was resistance was less. So when I change the material also, I find a difference. When I changed the area also, I found a difference. When I increase the length also, I found the difference. So put everything together. So it was observed that we finally concluded that the resistance of the conductor depends on its length, on its area of cross section. This area of cross section I also call it as thickness, which is always the circle formula pi r square, then on the nature of its material. But on a precise measurement, to make it accurate, I only use the length, and I will say, you see, when I want to show it accurately, we know when the length is increased, when it become 2L, current increased. So it's directly proportional to the length. The currents are decreased here. When I increase the length, the resistance increased. So the resistance is directly proportional to the length, because when I increase the length, my resistance increased, and inversely proportional to the area of cross section. That is, when I increase the area of cross section, my resistance become half. So that is what they say. So always remember, when the resistance increases, current decreases. When the resistance increase, current decreases. When the resistance is less, increases. So put together, I come out with the formula R is equal proportional to L by A. As I said, to make the proportionality sign equal to, I add a constant called rho, which is called as constant of proportionality, or it's called as rho, and also it is called as the electrical resistivity. It is called as the rho is called as the resistivity. I call this rho or constant of proportionality. So there is a formula for resistance now. It is rho into L by A. Now, when I come to again to the starting of the para of this page, you can see that the ammeter reading decreases. When the ammeter reading decreases, when the current will show less current, when I increase the length of the wire, you see, the ammeter reading decreases to 1/2 when I increase the wire of the length. When I increase the length of the wire, when I increase the length of the wire is doubled. So that's what I have shown in the table also. When I put TL, my current is halved and my resistance is doubled, because it is directly proportional. You see, now the ammeter reading is increased. My current is high. When the current is high, when I used a cross section area, when I increase the cross section area, so the ammeter it is high when a thicker wire of same material. So thicker wire means nothing but thickness refers to the cross section area. So I have used, instead of A, I have used 2A. My current is increased, but the length is same. And when the current is increased, I know the resistance is halved. That is the reason I say R is inversely proportional to the cross section area. So the final understanding is resistance is directly proportional to the length, inversely proportional to the cross section area or the thickness, and resistance also depends upon the material, nature of the material. And final is the resistance also affected by the temperature. The resistance also varies with temperature, meaning if the temperature is increased, the resistance also increases. That is the reason when we talk about Ohm's law, I said when you define the Ohm's law, you should say temperature is kept constant, because the temperature affects the resistance also. So then this row is called as the resistivity. Hope this is clear. That is what what is resistance and what are the factors the resistance depends upon. Hope this topic is clear. We'll move on to the next topic, that is what is resistivity and resistor in series and parallel connection. Thank you.